Uh, Welcome back, everybody. With me, Ferry of Rinaldi. Uh, so the chapter that we will discuss on this video is the duality theorem. And as you can see from my slide, the the materials of the video comes from the textbook Linear Programming by Chofatal and Linear Programming and Network Flows by Mokhtar S. Bazara and friends. So in order to explain the duality theorem, I will use the following uh, example. So we start with the max problem. So I'm gonna copy the problem into Paint. Okay, it's not good. Okay, so this is the problem. So we have a maximize problem for x1 plus x2 plus 5x3 plus 3x4, and we have 1 2 3 constraints and the non-negative constraints. The thing that I'm gonna do is that this constraint number 2, okay, constraint number 2, I'm gonna multiply it by 5 over 3. So the thing that I'm gonna do is that I'm gonna multiply 5 over 3, 5 over 3 times 5x1 plus x2 plus 3x3 plus ax4 less than or equal to 55. Okay, so what we're gonna have is that 25 over 3 x1 plus 5 over 3 x2 plus 5x3 plus 40 over 3 x4, and that should be less than or equal 275 over 3. Okay, so now let's compare the coefficient of x1, x2, x3 and x4 that we have here with the second constraint with the coefficients of the variables in the objective function. And we can see that 25 over 3 is bigger than 4, 5 over 3 is bigger than 1, 5 is equal to 5, and 40 over 3 is bigger than 3. So we can conclude that if we solve the original problem, this problem here, and we get the objective function value or the z star, and based on that fact that 25 over 3 is bigger than 4, 5 over 3 is bigger than 1, 5 is equal 5, and 40 over 3 is bigger than 3, then we are sure that z star will be less than or equal to 75 over 3. So we can say that this 275 over 3, it is the upper bound of z star. Now let's do other thing. Let's add constraint number 2 and constraint number 3. So we add the two constraints. So 5x1 plus minus x1, that's 4x1 plus 3x2 plus 6x3 plus 3x4, and that should be less than or equal to 58. And now let's compare the coefficients of x1, x2, x3, and x4 that we have here with the coefficient of x1, x2, x3, and x4 that we have in the objective function. So 4 equal 4, so and 3 over here is bigger than 1 over here, 6 over here is bigger than 5 over here, and 3 is equal 3. So we can say that if we solve the original problem and we get the value of z star, and the value of that z star must be less than or equal to 58. So this 58 is another upper bound of the z star, but this one, the 58, is a better upper bound. So what we are doing here is to get the linear combination of the constraint, and we compare it with the z star. So based on this fact, we can conclude that for the max problem, so the conclusion based on this fact for the max problem, so the z star will be less than or equal to the linear combination of the left hand side of the constraint and the left hand side of the constraint must be less than or equal to than the right hand side of the constraint. The right hand side of the constraint. Okay. Okay. And the statement that I have over here, we call it as the weak duality theorem. So this is what we call as the weak duality theorem for the max problem. Okay. So if I come back to the slide, I have the statement of the weak duality theorem for the max problem. And this is it. So z star is less than or equal to the linear combination of the left hand side of the constraint, and it is less than or equal to the linear combination of the right hand side of the constraint. So mathematically, so Cx is less than or equal to Wax, and Wax is less than or equal to Wb. And from the revised simplex method, we already know what W is. Now for the mean problem, it is just the opposite, the weak duality theorem. So z star must be bigger than or equal to the linear combination of the left hand side of the constraint, and that is must be bigger than or equal to the linear combination of the right hand side of the constraint. So that's the weak duality theorem. Now I'm gonna come back to the problem that we have over here. So what I'm doing here is that I just multiply the second constant by 5 over 3, and then I just add constraint number 2 and constraint number 3. So I am not doing this in a structured way. So now let's do this in a structured way. Okay. what I'm gonna do, I'm gonna copy this problem again. Okay, so what we have, so the problem is max 4x1 plus x2 plus 5x3 plus 3x4 and then subject to x1 minus x2 minus x3 plus 3x4, and that is less than or equal 1. Then 5x1 plus x2 plus 3x3 plus ax4, and that should be less than or equal 55. And the last one is minus x1 plus 2x2 plus 3x3 minus 4x4, and that should be less than or equal to 3. And the non-negative constant x1, x2, x3 and x4 must be non-negative. So this is the problem. So the thing that you need to remember is the weak duality theorem. So in a weak duality theorem, for the max problem, so this is it, the weak duality theorem. So the z star is what the z star is less than or equal to the LC linear combination of their left hand side, and that should be less than or equal to the LC linear combination of the right hand side. That's the only thing that you need to remember for the max problem. So what I'm gonna do now is that I'm gonna get the linear combination in a structured way. So the thing that I'm gonna do, I'm gonna multiply the first constraint by W1 and multiply the second constraint by W2, and then I'm gonna multiply the third constraint by W3. Okay, so I'm gonna add parentheses over here. Okay, that's fine. So see that, so it says that the linear combination of the left hand side, this is the left hand side, so this is the left hand side, must be less than or equal to the linear combination of the right hand side. See here in our statement, the left hand side is less than the right hand side, so it is following the weak duality theorem. So in order not to change that, so W1 must be positive, because when W1 is not positive, if it is a negative, then the sign will change. So the same thing with this the second constraint, so W2 must be positive also, and W3 also must be positive. Okay, now let's do the multiplication. So we have, so what I'm gonna do, I'm gonna multiply, so W1 times 1x1, W2 times 5x1, W3 times minus 1x1. What I'm having there is W1 plus 5W2 minus W3 everything time x1, and that should be, so according to the weak duality theorem, so the linear combination of the left hand side must be bigger than or equal to the z. So since it is x1, so that should be bigger than or equal to, so this is the coefficient of x1, so that thing must be bigger than or equal to 4. Okay, now we need to pay attention here. So x1 is positive here, x1 is positive, so when we multiply, so this is 4x1, so when we multiply everything by a positive number, so this sign will not change, so we are okay over here. Okay, so here we can cancel x1. Okay, we do the same thing with x2, so we're gonna have w1, no, minus w1 plus w2 plus 2w2 times x2, and that should be bigger than or equal to, so according to the weak duality theorem, bigger than or equal to x2. Okay, so since x2 is positive, so nothing will change, so we are good with the sign, so I can cancel this and this become 1. And now for the x3, we'll do the same thing, so that will be minus w1 plus 3w2 plus 3w3 times x3, that should be bigger than or equal to 5x3, and then same thing with x4, that will be 3w1 plus 8w2 minus 5w3 times x4, and that should be bigger than or equal to 3x4. Okay, so since x3 and x4 they are both positive, so we are good over here, the sign will not change, so I can cancel x3, I can cancel x3 over here, I can cancel x4, and I can cancel x4 over here. Okay, so the last thing that we need to do is to multiply w1, w2, w3 with the right hand side. So what I'm having over here is w1 plus 55 w2 plus 3 w3. Okay, now see, so we have w1, w2, w3, they are non-negative, and here it is just like a set of constraints. And what about this guy? So w1 plus 55 w2 plus 3 w3. So when we come back to the weak duality theorem for the max problem, so z star must be less than or equal to the linear combination of the left hand side, and it should be less than or equal to the linear combination of the right hand side. So when we draw it, so it will somehow it is like this, but it is not correct because we have a non-linear function over here, but it's okay. So this is the linear combination of the right hand side, and this will be the upper bound of the z star. So what we want to do with the upper bound, we need to move it down so that it will near to z star. So we want to make it smaller, and that means we want to minimize the upper bound, or we want to minimize the linear combination of the right hand side. So we want to minimize this function. Okay, so what we are having right now, it is just another linear programming problem, which is a main problem, and that is minimize w1 plus 52 w2 plus 3 w3 subject to w1 plus 5w2 minus w3 and bigger than n equal 4 minus w1 plus w2 plus 2w3, sorry, this should be w3 bigger than or equal to 1, and then minus w1 plus 3w2 plus 3w3 bigger than or equal 5, and the last one 3w1 aw2 minus 5w3, and that should be bigger than or equal 3, and the non-negative and the statement for the decision variable or for the w, so w1 w2 comma w3 bigger than or equal to 0. So we just get a new LP problem. So we can conclude that for every LP problem there is another LP problem that we can develop. So when we call the original LP problem as the primal, this is the primal LP, and the other LP problem that we can get from the primal one, we call it as the dual LP. Okay, so what is the dual of the dual? It is just the primal. So what I just show you is that how to construct a dual of from an LP problem, and this is for the max problem. So we can do the same thing for the min problem by applying the weak duality theorem for the min problem. So now let's do another example, and for this example we will get the dual LP from a min problem.